All right, folks. We're beginning our last session. Okay. So I think we're done with this. So I need to show you a thing or two about this. Now I realize that you perhaps have not done this before. So how do we calculate how do we locate point of inflection? We know now we don't know the location, but we know at that particular location moment is 0. Just like this. We don't know where, but we know at this location shear is 0. So the best way, I suppose, to locate the point of inflection is by cutting this free body diagram here. Okay? And draw the free body diagram again. Oops, sorry, not very straight. Doesn't matter if it's a circle or rectangle before. So when I have a free body diagram, I know that this is 3, 1, 1, 2. I know that this is 2, 0, 7, 5. I know that this moment is 0. Then there's shear here, but I don't want to know how much it is. Therefore, I'm going to take the moment here to eliminate this shear, right? One thing remains is that this X. How much? Moment is 0. Shear, we don't know, but we don't care. So when we take the moment at this particular location, you will have moment equals 3, 1, 1, 2 X minus 2075 multiplied by X square over 2. Somebody calls me now. Probably have some, how do you call it? The phone call, junk phone call, you call that? Scam? Yeah, whatever. Okay. So that becomes your equation. And you know this is equal to 0. And you can solve it. That's how we can locate the point of inflection. Okay. Realize that this is a quadratic equation, so you have 2 answers. And when you see the numbers, you should be able to tell which number is your answer. Okay. You see, when you take a break and you just, cannot stop your break, you're missing something. Okay. All right. So that's one thing. The second thing, you guys get the one thing, where I can move to the second thing. The first thing, the second. Now, the second thing, oops, sorry, I just couldn't stay still, can I? Actually should get up and walk, because when you get to my age and you sit too long, you have a lot of gas in your stomach. Okay, it gets like something like the stomach ache sometimes. Okay, so that's you should cover it. Some of your friends still making some notes. Okay. Now we know the point inflection. It's important because it's a location where the moment becomes 0. So it's a good point to connect your beams if your beam is very long and you cannot make it like a one long beam. Okay. Now, the point A and B here. Remember, B2 has to be supported by B1 here and here. So that's where the reactions will go. So now if I draw this, hello, okay. So now if I draw this beam, what? This one. What's gonna be your free body diagram? Now, it's like playing games, really, because it's not difficult. It's not mathematically difficult. You just need to see the system and understand how you are going to take care of your structure. So when you look at this B1, you know, actually I meant to call this beam B1. So let me get that off first. I meant to call this, oh, sorry. I meant to call this B1. It's easier. So if that's your B1, your free body diagram is simply this, right? And with the load. So now if we look at this as another B1, you see you need to have the cantilever portion. Because if you don't have the cantilever portion and you say, okay, I'm just going to build this beam separately and do it like this, it means that this cannot be a column. A column is not strong enough to give you the fixed support. This is a column. Okay, this is the column. The column itself cannot be portrayed as a fixed support. You need to have something very, very strong, such as something they call shear wall. Do you know what it is? It's a structural wall. The walls in your rooms, generally like that one, or the ones in your bedroom, if you stay in the bedroom, folks at home, they are not shear wall. This is a wall, just a wall, not ice cream, just a wall. Okay, it's I don't know what to say. It's just a non-structural wall made of bricks. They cannot sustain any load. They're just there to break the rules. Okay, when you have the structural wall, because they generally take lateral shear, they call it shear wall. It's part of the high-rise building in this country. It's a wall that is built with the reinforced concrete, with the reinforcing steel inside. So it's a very, very strong structural system. That shear wall can be rendered or thought or portrayed as a fixed support like this. Okay. Come on, yeah, take care of it. All right. If it's column like this, no, you cannot look at it and say it's a fixed support. So that generally means your B1 here. Now, after I talk to you, take it off because I can't see it here. OH, you know. For this B1, you have to make sure that the beam extends out to take care of B2. So that means the reaction from, guys, miss a lot. Reaction from B2 will be here. This part of B1, you must make sure that it is strong enough to take whatever the reaction that is from B2. Okay? Do you feel it? It's your job to make sure that you design this B1 strong enough so that it can actually support B2. You can do that by including the reaction from B2. So therefore, the moment generated here will be the moment generated by the reaction from B2. So when you design this beam, You know, whatever the size of the beam or details of the beam that you have, it's going to be strong enough. And then, you know, the system will take care of itself. Question, if any? Hello? So, you guys taking notes? Can I go on, finish? If you look at B1, you see it's a beam, right? So it has a weight. So the self weight will cover all the length. And then you have another B2 on this side as well. And then you have the floor. Just this area, right? But not at the overhanging area, because the floor is placed in the other direction. So any question? Yeah, actually, I screamed less this week, right? It's better. Ooh. Okay, so I can proceed, perhaps. All right, yeah, all right. So let's take a look at B1. So we have a typical B1 without a cantilever portion that looks like that, and then we have the B1 with a bit of a cantilever portion. Right here, the W is simply, okay, that's, I don't have enough space to write, but anyway, that's 600 plus 1500 multiplied by the tributary width, which is how much? I think it's kind of 2, right? Do you agree? 2 meters becomes a tributary width, just like this, right? There. Yeah. So be careful here. If you're gonna get it wrong, you're gonna get it wrong here. You know, the tributary width, seen it before. Then plus the weight of the beam, which is how much? 500, right? Thank you. But for any other B1 with a cantilever portion, you will have this 600, 500 as a self weight throughout the beam. And then may I change the color a little bit? This is 600 plus 1500 multiplied by 2. Right? Be careful. It's not difficult at all. You just need to be thorough and careful. And don't forget that we need to also place the reaction from B2 here. And that's going to be 3112, right? Forgive me for I sometimes don't write the unit. Okay, actually you should always do it. oh, sorry, kilogram force per meter. Any question? Yeah, one thing missing from the online class as well is that I don't see students right. So I tend to go very quickly. Now I can see you right. I can see your attention, where your attention is. So I can pick up the right pace. So that's 2100 multiplied by 2. So this blue one is actually 42, right? 4200 multiply add with 500. So in fact, this is 47. Correct? Any question? Oops. You know what? If I need to talk to the microphone all the time, why don't they have something that can hold on to the microphone for me? Because this is not light, you know? The microphone is heavy. Try holding it for 3 hours. My hands are shaking, really. We better have something, right? They have it, don't they? Maybe you can use a headset like this. Yeah, right? Like in the concert. Damn. You know what? How do you like that? It's too high, right? That makes maybe I try to find some. Anyway, kind of, yeah, maybe I developed some muscles. Okay, so we have that, and I think it's 4 meters. Really? Let's check. Not sure. 6 and 1.5. And that's 1.5. And you know, you better write the length of the beam as well. Okay, so that we know what you're talking about. For the first one, you know, please, if you come this far in your life, you better be able to calculate the shear and the moment right away without any hiccups, right? And you know what? Every year, some students got it wrong. I can't believe it. Do you know that if this is L, this is W, the shear is WL over 2, and the moment is WL square over 8, right? Correct? This is like a gimmick. And you should even know the deflection is 5 over 384 WL to the power of 4 over EI. Because that we do it every day. But you don't have to remember this. It's just like showing off. No, it's not showing off. I don't show off. It's giving you the feel of what you can do, what you should be able to do when you become a true engineer, professional. You go out in the real world and, oh, uniform load, simple beam, maximum shear, maximum moment, maximum deflection. Should go out like that. When you talk to professionals, you know, oh, I don't remember. I don't know this. I don't remember that. I need to calculate this first. Give me 10 minutes. I can give you maximum moment. They're not going to wait for you, right? Especially the day and age of iPhone, Samsung, whatever, Galaxy, whatnot. Okay, so for that typical, you should know that M max Oops, sorry, I should write shear max first. V max is WL over 2, so it's 47 multiplied by 6 over 2, and max is WL square over 8, 4700, 6 square over 8. This is your professional career. But I will say it's okay because not everyone likes to be a structural engineer. That's understandable. So if you become maybe a water resource engineer, the coastal engineer, like my wife, doing things I never understand, using the sine curve to imitate the waves. Can you imagine that? How can you do that? And it's not just the trigonometry function. They use the hyperbolic trigonometry function as well to simulate the curve. I would never understand it until I die. It's impossible. But they do that. Thanks to a guy called Fourier, long time ago. The guy went to Egypt and was impressed by the heat wave. So he came up with the formulas to, so that you can write every wave in the world with the Fourier series and combine them. But without the Fourier series, you know what happens? You could never have your mobile phone nowadays. It's all based on Fourier series. You believe that? So it's not about crazy mathematics all the time, So, okay, anyway. And Vmax here, this typical B1, you guys need some time. This B1, listen to me, this reaction here, which is this one, right, will have to be supported by B3, right? Right? It doesn't go anywhere because they are not directly into the column. So it will have to be carried by B3. Can you see that? So you must include the reactions from this typical B1 onto your B3 so that the moment that you have for B3 will cover the weight from B1. Or I should say the reaction from B1. So you can use that moment to design structure safely. Any question? So now while we are at it, may I have the number, please? It's just 47 multiplied by 3, right? Okay, so that is going to sit on B3. Yeah. Now you need a little work for this B1. Now one more thing I'd like to tell you. This is the old practice that I did when I just graduated, and I worked in a company that the seniors are very good to me, and they were very professional. When they call the beam names like this, I was taught to call this something like B2. And then this portion, I will call it B2C. C stands for cantilever, so that I know this is a cantilever beam. And I can give the proper details. And when you look at the construction drawings, you would know that, okay, this is cantilever beam as well. But I don't think many people do it nowadays. And I use the same beam B2 and B2C because they are continuous. That I know. Okay, so in here, I would call it B1, and then this becomes B1C, and then this is B1C, so that I know it's cantilever. That's the old practice that I use, I like it. That's why I tell you. You may not call it like this because nowadays some people call it B1 and then they call this B2, you know. Maybe. Or they call this B5. And then they give details, you know, the continuous part of B1 and B5, you do this kind of reinforcement. I don't like it. It's confusing. So if you don't like something, don't do it to others. And that's only normal thing to do, right? Okay, so you may need a little work on this. I leave it to you. I'd rather talk about B3 first before the time runs out, because I believe you can do it yourself. This beam, it's easy, and it's symmetric. So you should know the symmetric structure should give you like the mirror image, you know, left and right, right? And that beam, easy enough. And you know, you should do it and then compare the positive moment to the one that you have here. You're gonna learn a lot from that. So for that beam, your shear force should look like this. Right? And your bending moment diagram like that. Some sort. You can expect that, right? From the load pattern. And the slope here is going to be more gentle to the one here because the load is different. Right? That's what you can tell right away. You can do it yourself. I believe it's in the YouTube channel as well. Do it and then check with the numbers. So now we are ready to make our final journey to see what B3 is all about. Yeah, okay. Some of your friends still making some notes. Any question before you move on to B3? I just can't even, you know, rest my back. Okay. So B3 now. I better erase a lot of things, right, to clean up the area so that you can see better. All right. So this is our B3. Maybe I can use some fancy color. Blue it is. Okay. Ladies and gentlemen, first thing first. Now you know B3 has to support the reaction from B1, correct? Anyone want to ask me something? Come on. No question. Okay. Let's say now you know this B3 has to support the reaction from B1 here. And you must not forget that you have to extend this to support this as well. But we haven't mentioned this beam. Okay? So actually, before you could write the free body diagram of this B3, you need to calculate this beam. Correct? To know the reaction of this beam. To put on your B3. So B3, we have 3-point loads. Yeah, 3-point loads. 2 from B1 and then 1 from another beam that we don't even name it. Okay? And now, the very important thing. B3, you can see that it has 2 spans. So, in the real world, if it's a concrete beam, or if it's a beam in the part of the structure frame, steel structure frame, we don't analyze this as a simple beam. We will analyze this as a continuous beam. So what you actually see is something like this. You have reaction from B1. And then you have this. You don't know what it is. What else do you have? That's like playing games. What else do you have? Okay, let's wait for you to catch up. Oops, sorry. Okay. Nobody's talking to me. So, yeah, the class is on so they can see your face. All right. What else we have? Now, see, again, this is not about, being difficult or anything. It's about being thorough, being careful, check all the loads. You look at B3 yourself, you will see that, hey, actually, this is tiny part of the floor, right? That half of it is carried by B2. So another half is on B3. So you must not forget that. But then again, B3 will have its own self weight. And then the load from the floor outside on this bay and that bay. I have because we begin late today, so I asked you to stay with me for maybe a few extra minutes. So because I like to finish this, okay, so that everything is on the video nice and tidy, and just like something is missing. Okay, so let us now you see it. So I'm just gonna move on to the new page and write it again because I ran out of space. Okay, you have questions maybe? You look like you may have questions, but afraid to ask. Let me tell you again. I say every year, the worst question, the most stupid question, is the question that you don't ask. Don't be afraid that somebody will say, "Hey, why you ask this? You don't get it. You don't care about other people. What others think. You only care about the answer that you need. You don't have to care about what others think. Okay, you need to only care about your own understanding. And many times, it's a question that everybody has in mind, but nobody speaks up. Okay, so let's move on. And here we go again, glasses off. So it's B3. You see, can't make up my mind. Triangle or circle. Oops, why I take my mask off? Feels more familiar. This line is crooked. Let's draw again. I can do this. Yeah. Okay. And then the proportion is bad. So let me try to erase this. Hey, okay, right. So that's a green load. And that's a red load. This red load is from B1, so it is, yeah. Right? And then you have the self weight. I can say here self weight 500, right? And then you have the floor. Which is exactly the same number as the one on the your B2. So bear with me. I need to try to go back and see so that you have the feeling. But this is the load included the beam weight. So hey, you know what? I forgot to include the beam weight here, right? Is that correct? Ah, poor thing. Or did I include? Oh, okay, I did. So, but that blue load is just this. Okay, so we need to do new calculation. So that's 600 plus 1500 multiplied by 0.75. Okay. So if you please give me the number. Okay, 1575. Thank you. So now you better give the proper dimensions. This is 3. This is 3. This is 3. This is 3. This is how much I don't remember. But better keep look. 2. Okay, so that's B3, but it's not finished because we need to calculate the green load here. And the green load will have to come from, I'm making notes here. Oh, it's 2, right? Yeah, sorry. Yeah, you're right. I guess and I guess it wrong. Sorry. So it better be 2. Thank you. I just only want to check if you're asleep or not. Okay, sorry about that. Okay, so ladies and gentlemen, one more thing. You guys are making notes. Please, more things. But one more thing, 2 more things, doesn't matter. So okay, we ready? Perhaps. You will see that this beam actually has has 1, 2, 3, and 4 reactions. Okay. So now the number of reactions exceeds the number of equilibrium equations that you have. So this structure is called statically indeterminate structure. You cannot determine everything by simply using statics. You need new method, which you will learn in due time. Okay. Now let us focus on the green load. I have to go back because I can't remember. Okay. So for this beam, here it looks like that. Okay, without the load. So the green load here, you're gonna have to help me because I don't remember. Okay. Something like that. And of course, it has its own weight. Self weight 500. And then the floor in the middle here is, of course, 600 plus 1500 multiplied by 1, right? Because the width is 2, so the tributary width that this beam has to be responsible for is half of 2, so it's 1. You can go back and take a look at the floor plan again. Sorry. Here. That is the tributary width. Half of the 2. Okay? So that's that. So we can actually easily calculate this. That is 6 meters, right? That's how much? 1.5. Thank you. So now the reaction can be easily calculated because it's symmetric. So we have 2100 multiplied by 3 plus 500 multiplied by 4.5, right? That R here is that R. Then we're done. Or you give it the number, right? How much? Say again, please. 50. So your fun has begun. So I have eaten up your time for 6 minutes. Hope it's okay. Please ask questions. And if you don't want to ask me anything, let me stop the record. Otherwise, it will get too long. Okay.